whenever we are having a symmetrical frame, we need not consider the lateral sway component into the consideration. So whenever we need to calculate the stiffness, we know that we have to consider the far end conditions. The rotation contributions are only calculated for the intermediate supports and not for the end supports. So hello everyone, welcome to Civil Galaxy. Myself Dr. Pruthviraj B S. In today's session, we shall see how to analyze a frame with the help of Kanis method. So here I have considered a frame having a single bay and 2 stories. So if you observe the frame closely over here, the length of the column AB and CB are identical to the length of the column DE and EF. And if we cut this frame exactly at the center, we are going to get an identical mirror image, which means, to be very specific, this particular frame can be called as a symmetrical frame. So from the previous classes we have learned that whenever we are having a symmetrical frame, we need not consider the lateral sway component into the consideration while we are analyzing the frame, which means if the frame is symmetrical, what we can do here is we need not consider the entire frame for analysis. Either we will consider the left portion or the right portion for the analysis. So from the previous classes we have learned in Kanis method, the first step will be to calculate the fixed end moments. Fixed end moments. So as we discussed that either we can consider the left portion or the right portion. Here in this case I will consider only the left portion over here. So we need not consider the right portion, which means we need not calculate the fixed end moment for the right portion. Only for the left portion we will calculate the fixed end moment, because the right portion we will not use anywhere in the further calculations. So if we see here, for span AB there is no loading, so the fixed end moment from A to B and fixed end moment from B to A. Also if we see here, for span CB, since there is no external loading, so the fixed end moment from B to C and fixed end moment from C to B will be equal to 0. So next if we come for the span BE over here, the fixed end moment from B to E will be equal to, since it is carrying an UDL and we are calculating only for the left portion, so from left to right the sign convention is negative and the formula is minus WL square upon 12, since it is carrying an UDL. So if we just put the values over here, W they have given, which is minus 24, into the span here length is 4 meters. So 4 square upon 12, which will be equal to minus 32 kilonewton meters. Next, if we come for this portion over here, if you observe for span CD, from C at a distance of 1 meter we are having a concentrated load of 20 kilonewton, and at a distance of 1 meter from point D we are having another concentrated load of 20 kilonewton. So in that case, the fixed end moment from C to D, the formula will be minus W A B square upon L square minus W A B square upon L square, since it is having 2 concentrated loads. So this will be the first one here. If you see here, for 20 kilonewton, so W here is minus 20 and the distance A, so this will be the distance A here, and the remaining from here to the point D will be the distance which is for point B. So this will be 1 into 3 square, because the total length here is 4 meters. Out of that 4, if we take out 1 meters, the remaining will be 3 meters upon the total length here is 4 square minus 20 into, for the second load over here, now the distance of A will be from this point to this point is 3 meters. So it will be 3 into B will be 1 square upon L square, that is 4 square. So if we just calculate this one, fixed end moment from C to D, we are having a value of minus 15 kilonewton meters. So this is the value. So the second step will be to calculate the stiffness, which is represented by K, and rotation factor. So for step 2 will be to calculate the stiffness which is represented by K, and rotation factor which is represented by U. So to calculate the stiffness and the rotation factor, from the previous classes we have learned that we need to consider a table, which the first one will be the joint, and for that particular joint we have to consider the members, and for that particular member we need to find out the relative stiffness, that is K, and then we will calculate the total stiffness which is represented by sigma K, and lastly we need to calculate the rotation factor which is represented by U is equal to minus half into K upon sigma K. So now if we just observe over here, since we are considering only the left portion over here, we are having B and C, that is two joints. So we are having two joints, that is B. First we will consider only the joint B over here. If we observe joint B, B is connecting to member BA, and B is connecting to the member B to E, and B is connecting to the member B to C. So we are having three members, that is B to A, B to E, also from B to C. These are the three members. So if we take the joint C over here, we are having two members, that is from C to B and C to D. So C is having two members, that is C to B and C to D. See here, now if we observe, I will explain the concept when it comes. So first we shall calculate the stiffness one by one. So whenever we need to calculate the stiffness, we know that we have to consider the far end conditions. So for member BA, if we take the member BA over here, B is the near end and A is the far end, and since A is fixed here, the stiffness is equal to I by L. Whenever we are having a fixed support, the stiffness will be equal to I upon L. So I they have provided here, that is 2I upon the length they have given, which is 4 meters. So if we calculate this one, we are having a value of 0.5 I. Now if we take the member BE over here, so B to E, it is having a length of 4 meters, and the moment of inertia they have given here is 4I. See, if you observe the far end condition over here, B is the near end and E is the far end over here. Since E is an intermediate support, in structural analysis, even the intermediate support is also considered as a fixed support. So the the stiffness will be equal to I upon L. But since we are taking only one portion here, the stiffness we need to consider half of the value only. So if we take BE here, which will be I upon L, since the far end is fixed here, but we are taking only the half of the value, so it will be half of I by L. But the length should be considered as it is, the total length. So here I they have provided, that is half into 4I upon 4, which will be equal to, the value here is So again it will be 0.5i. Now if we come for span, so remember BC over here, B is near end and C is far end over here, and since C is an intermediate support, it is also considered as a fixed support. So for fixed support, the stiffness is equal to I upon L. So I they have provided here, which is I itself, the value here, upon the total length is 4 meters. So which will be equal to 0.25 I. So now if we add all these three, we are going to get the total summation, which will be equal to 1.25 I. So now if we just put the value over here, that is U is equal to minus half into K upon sigma K to find out the rotation factors, we are getting a value of minus 0.22, minus 0.2 for member BA, and for member BE we are having a value of minus 0.2, and for member BC we are having a value of minus 0.1. So whenever we add this one, it should be equal to 0.5. That means this, for this joint and this member CB and CD, the total should be again 0.5. So the total rotation factor should be always equal to 1. So if we take the member CB over here, since C is the near end and B is the far end, since the far end is intermediate support over here, we are taking it as a fixed support. So the stiffness will be equal to I upon L. So the value of I for CB they have provided here, that is I upon the total span here is 4 meters, which will be equal to 0.25 I. So now if we come for span CD, C is the near end and D is the far end, and the far end is intermediate support, we are taking it as a fixed support. So the moment of the stiffness will be equal to I upon L. But since we are taking only one portion over here, the stiffness, the value of moment of inertia, we are taking it as half. That is, the stiffness we are taking it as half the value of the stiffness, which will be equal to half of the value of I they have provided here, which is 2. So here it will be 2I upon 4, which gives a value of 0.25 I. 0.25 I. So now if we take the summation of these two, we are getting a value of sigma K, which is 0.5 I, and if we just put the value over here for rotation factor, we are getting minus 0.25 for member CB, and for member CD we are having a value of minus 0.25. So the next step will be here to calculate the rotation contributions. So for that I have considered a table over here, which is also called as Kanis table. So what we have done here is we have just represented the intermediate supports with the help of boxes called as Kanis boxes, because the rotation contributions are only calculated for the intermediate supports and not for the end supports. So since we are calculating only for the left portion over here, this is A and this is B, this is C and this is D over here, this is E. So what we will do in this table here is, first we will represent the fixed end moments, whatever we have calculated in the first step. So we know that from A to B the fixed end moment was 0. Similarly from B to A also was 0. B to C was 0. C to B was 0. And from B to E we had a value which is minus 32 kilonewton meters. So similarly for C to D we had a value of minus 15. So in this boxes, what we will do here is we have to take the summation of the fixed end moment for this particular joint over here. So if we take joint B here, so here it is 0, here this is 0, and here it is minus 32. So if we take the summation of these three, we are getting a value of minus 32. So the summation of fixed end moment about the joint B is minus 32. Similarly, for joint C here it will be minus 15 and 0 it will be minus 15 over here. So now inside this boxes, what we have to write here is we have to write the rotation factors whatever we have calculated in the second step. See here, for member B to A we have got the rotation factor value as minus 0.2. This is minus 0.2. And for B to E we have got a value of minus 0.2, and from B to C we have got a value of minus 0.1, and from C to B we have got a value of minus 0.25, and from C to D we have got a value of minus 0.25. So now if you want to calculate the rotation contributions, which is represented by m dash, so here I need to calculate m dash AB, and here we need to calculate m dash B to A, and here it will be m dash B to E, here it will be m dash E to B, and here it will be m dash B to C, here it is m dash C to B, and m dash C to D, and m dash D to C. So as we have discussed earlier, the rotation contributions are only calculated for the intermediate supports and not for the end support. So the end support, it is m dash DC, m dash EB, and m dash AB will be equal to 0. See, we know that whenever we want to calculate the rotation contributions, we know that the formula which is given by, that is m dash is equal to U into summation of fixed end moment plus summation of far end rotation contributions. This is the formula we need to use whenever we need to calculate the rotation contributions. So if we consider for joint B over here, we are having m dash BA, m dash BE, and m dash BC. We know the summation of fixed end moment for joint B here is 32, which is minus 32. So if I need to consider m dash BA over here for joint B, which is the far end over here, see here, right here the representation, m dash AB will be the far end. Similarly, m dash EB will be the far end over here if we take here, and m dash BC will be the far end. So for joint C, here m dash DC will be the far end, and here that is m dash BC will be the far end. So based on this one, now if you want to calculate the rotation contributions, first for m dash BA, see here, for m dash BA we are having from B to A, the rotation factor value we have got here how much? Minus 0.2. Summation of fixed end moment we have got here, that is minus 32, plus, which is the far end rotation contribution now, m dash AB, m dash CB, and m dash EB. Since m dash AB and m dash EB are the far end rotation contributions, and it is the end supports, so the value here is 0 for both, it is 0 plus 0, plus here m dash CB, we don't know the value for the first cycle, we need to calculate. So it will be also 0. So which gives a value of, so plus 5.65 kilonewton meters. So this is the value. So this value, that is m dash BA value, we write over here, that is 5.65. Next, if you want to calculate for m dash BE, so m dash BE, which is minus 0.2, that is the rotation factor over here. Rest everything remains same, that is the summation of far end, fixed end moment remains same. Summation of the far end rotation contributions also remain same. For joint B, it is m dash AB, m dash CB and m dash EB. So for the first cycle, everything is 0 over here. We are getting the same value again, which is plus 5.65 kilonewton meter. So this value will just write over here, that is 5.65. Next, if you want to calculate m dash BC, so for m dash BC, the rotation factor value here is how much? That is minus 0.1. Rest everything remains same, the value, which is minus 32 plus 0 plus 0 plus 0. We are getting a value of plus 2.83 kilonewton meters. So this value we will write over here, which is 2.83. So next, if you calculate for m dash CB, so m dash CB, we are having the rotation contributions as minus 0.25, and the summation of fixed end moment over here is how much? It is minus 15. So if we take the far end rotation contribution, now for m dash CB, the far end rotation contribution here is m dash BC. For m dash BC, we are having a new iteration value, which is plus 2.83 plus the far end rotation contribution, it is m dash DC is 0. So it will be 0 over here, which will be equal to, gives a value of 3.75 kilonewton meter. So here, so we are getting a value of 3.75. Next, for m dash CD, so everything remains same over here, that is the rotation factor is minus 0.25 and minus 15 plus 2.83 plus 0, which will be equal to 3.75 kilonewton meters. So this value also will write over here, which is 3.75. So if we observe here, whenever the rotation contributions are same, we are getting the similar values over here also, and here also the rotation factor value is same and the rotation contributions value are also same. So this iteration value or the iteration process we need to go on calculating until we are getting the similar values over here. See here everything remains same, only the far end rotation contributions keeps on changing. So we will keep the rest as it is, only we will change the far end rotation contributions over here. See here, now for joint B, if we take, here it is 0 and here it is 0, so it will be plus 0 and plus 0. So here if we take, we are getting a new iteration value for the far end rotation contribution, that is m dash CB. We are having a new iteration value, which is plus 3.75, which will be equal to a value of 5.79 kilonewton meter. So this value we will write over here, 5.79. So next here it will be same, that's 0 plus 3.75. We are getting a value of 5.79 kilonewton meters. So as we discussed, whenever the rotation factor is equal, the rotation contributions value are also equal. So we'll write here that value 5.79. So m dash bc. So for m dash bc, the value will be plus 0 plus 0 plus 3.75, which will be equal to, it is 2.90, which is 2.90 kilonewton meter. So this value we will put over here, 2.90. So here if we take m dash cb, the far end rotation contributions, here it is m dash dc is 0, and if we come over here, we are getting a new iteration value which is plus 2.90. We are getting a value of 3.04 kilonewton meters. So here also it will be same, plus 2.90, which is 3.04 kilonewton meters. So this value will write over here 3.04, and here also it is 3.04. So now if you observe the values, they have changed. Here it is 2.83, 2.9, 5.65, 5.79. Similarly here 3.75 and 3.04. So we have to continue the iteration process. So going for the third cycle, so going for the third cycle over here, see here, here this will be 0 and here it is 0. So 0 plus 0, and here we are having a new iteration value, that is plus 3.04. So now we are having a value of, that is 5.80 kilonewton meter. So this value we'll just write over here, that is 5.80. And similarly here also we know the values will be same. So it is 5.80 kilonewton meter. So this value will provide over here, which is 5.80. So now m dash bc, so this is 0 plus 3.04. We are having a value of, for m dash bc, it is 2.90 kilonewton meter. So this value will provide over here, it is 2.90. Here for m dash cb, we are having a new iteration value over here. Rest everything remains same, which is 2.90, and here also 0 plus 2.90. We are having a value of 3.03 kilonewton meters. Here also it is 3.03 kilonewton meters. So this value will provide over here 3.03, and here also 3.03. So if you observe now, the values are almost similar over here, 3.04 and 3.03 and 3.04, 3.03, 2.9, 2.9. Here it is 5.78, 5.80. So now if you go for the fourth iteration cycle also, we will get the exact value. So this value we shall consider the final value as the rotation contributions to calculate the fixed end moments. See here, so these values. So these values we will consider it as the fixed end, the final rotation contributions to calculate the final end moments. So the next step will be to calculate the final end moments. See here. See here, the last step will be to calculate the final end moments So whenever we want to calculate the final end moments, we know for AB, for example, from AB, MAB, we know the formula, that is fixed end moment from A to B plus 2 times the rotation contribution about the near end plus 1 times rotation contribution about the far end. So in this case, MF AB, we know it is 0 because the fixed end moment from A to B is 0, we have taken over here, plus 1 time the rotation contribution is also 0. M dash BA value we have taken here, final rotation contribution value, which is plus 5.89. So fixed end moment from A to B will be equal to 5.89 kilonewton meters. So this is the value. So similarly, if we go on calculating the value for other members, I'll just write the value over here directly. So MBA is having a value of 11.60 kilonewton meter, and MBE is having a value of 8.83 kilonewton meters, and MBC is having a value of minus 20.40 kilonewton meters, and MCB having a value of plus 8.95 kilonewton meters, and MCD is having a value of minus 8.95 kilonewton meters. So see here, now we have got the values of the final end moments only for the left portion. So now if we take or consider the frame as it was earlier, this is a representation over here. So the frame was something like this, where this is A, this is B, this is C, this is D, this is E, and this is F. See now here, if we take A to B, that is plus 5.89, which is in the clockwise direction, we will call it as 5.89, and from B to A it is 11.60, that is also plus, means it is clockwise, so 11.60, and from B to C it is anti-clockwise, negative, which is 20.40, and from C to B it is clockwise over here, which is 8.95. From C to D it is anti-clockwise over here, 8.95, and from B to E it is clockwise, positive over here, which is 8.83. So now based on this value, if you want to represent the right side portion of the frame, see here, from C to D it is anti-clockwise, so this will be clockwise over here, which is 8.95. So from C to B it was clockwise, so here it will be anti-clockwise, which is 8.95. Here it is anti-clockwise, so here it will be positive over here, which is 20.40, and from B to E it is positive, so from E to B it will be negative, which is 8.83. So from B to A it is clockwise, so here it will be anti-clockwise, which is 11.60, and here it is clockwise, 5.89, so here it will be anti-clockwise, which is 5.89 kilonewton meters. So similarly, we shall see few more problems related to Kanis method in the next coming classes. Thank you.